Hello, Physics 4DS. We have a topic today, a closer look at the EMF. I'd like you to consider a conductor of length L that's a cursive L, not an I there, sorry, moving with velocity V through magnetic field B. So that means here I've drawn a north and a south. Now maybe this is from a horseshoe magnet, so maybe we can't see the rest of it. It's coming up and over, or it's underneath, or something like that. But we're creating a magnetic field here. The magnetic field would be coming this way, leaving from the north, entering at the south. Okay, we know that those would be the flux lines. So there's my magnetic field B. We have our conductor here of length L. Now, what's kind of interesting is this conductor might extend past the magnetic field, but just because it doesn't mean that it's going to be experiencing the magnetic field. We saw that the magnetic field strength drops off really quickly when we leave the pole faces, if you remember when we did that activity with the iron filings. So we actually only consider this area in here as the length. That's the only amount of the conductor that's experiencing that magnetic field, or that's in a magnetic field that's a uniform value. Now we know that it's moving. Let's say it's moving velocity V. Let's take this wire and move it with a velocity, let's say, into the page. I'm just picking that as random, but it, I could have said out of the page. I don't really want it to move side to side, because if I take that wire and I move it sideways along, I'm not going to see any change in the magnetic field. And if you've watched the other videos, one of the things that we've talked about, both Mr. Collinville and myself have said that we have to have some kind of a change in the magnetic field, a change in flux in order to induce the EMF. So if we take this wire and we move it, pretending my pen is the conductor, and I move it into the page, then I'm going to be slicing through the magnetic field and getting a change in that magnetic field that's happening. Okay, so let's write that down, what I was just talking about. So the EMF is induced. Now, this is titled A Closer Look. So I want you to think about those little electrons. They are sitting in the conductor, because obviously a conductor is made up of protons, electrons, neutrons, all those different things. I'm most interested in the electrons because the protons and neutrons, they're stuck where they are. They might get to vibrate a little bit, but they don't really get to move. The electrons are the things that are going to have the ability to move through the conductor. So here's these electrons, and they're going for a ride. They are experiencing a velocity into the page. Okay, so EMF is induced because the free electrons, I'm just going to short form electrons as that, hopefully that's okay, in the conductor are moving through a magnetic field. Now, if you remember from our previous unit, if I had a charged particle and I moved it through a magnetic field, a force was exerted on it. So if these electrons are moving through with some kind of velocity V through a magnetic field B, they will, I'm going to make this a comma instead, they will experience a force. Okay, so this is the important part. that the electrons experience a force. Now, let's see what that means. Now, first of all, because I'm looking at the electrons, I'm going to use my left hand, not my right hand, but my left hand, and I'm going to say that the velocity is going into the page, so my thumb is going into the page. My fingers are going to leave from the north and enter at the south, point that way, which means that my palm is facing towards the top of the page. So that means that we have some kind of a force acting on each of these electrons, acting towards the top of the page. I'm not sure if you can see the green very well, but it's moving upwards. Now this one would stop when it was outside, but each of those would be feeling a force because of that changing magnetic field they're experiencing. They are going to feel a force. Now, when they feel that force, they are able to move. Okay, so therefore, the electrons are forced along the wire. Creating, now what's going to happen? If I get a bunch of electrons, they're all moving to this one side, then I'm going to end up with kind of a negative end on this side. If the electrons have left, what they leave behind is a net positive charge. So if I have a negative end and I have a positive end, they just all due to that electron movement, they've now created a potential difference. And what's another name for a potential difference? Well, if it's going to create motion, we could call it an electromotive force. And if I have a connection for this conductor, then I will get a current. And a current, if a complete circuit or path is connected. If we don't have that connection, then we just get the potential difference, and that's all. Now, let's look at what would the magnitude of that EMF be? What would it be like? Okay, now magnitude, when we talk about magnitude, we know that that means we're looking for the amount of the EMF. So EMF depends on several factors. Let's talk about some of the things that we just did in our drawing. So what did we have? We had a conductor of length L. Sorry, it's disappeared off the page now. If I put more wire into the magnetic field, what's going to happen? Well, first of all, let's look at the length of the wire. Hopefully it's fairly intuitive that if I put, I'm not sure why I wrote a B there, if I put more wire in, I'm going to have more electrons that are able to experience that force, so I'm going to get more EMF, right? So increased length means I'm having more electrons available, more material available, so I should get more EMF. And then I obviously was like kind of thinking ahead of myself here. The flux density is another factor. Now, remember, I could also call that magnetic field strength. I'm not sure why I called it flux density right there. I'll write magnetic field strength as well. Probably I'm using flux density because we've talked about so much with a change in flux lately. So if instead of just this horseshoe magnet, maybe I had an electromagnet that I could vary the magnetic field, and maybe I increase that. If that gets stronger, what do you think is going to happen to the EMF? Hopefully it's also intuitive. I'm using a curly E there. That it would be directly proportional to the magnetic field as well. Now, there's also the factor of the velocity. Now, you could say speed. That would be acceptable because as long as we have movement, that's important. If, let's use the variable v for speed. And then if I move more quickly, that means we're seeing a more drastic change in the EMF. So then we should see E being proportional to V. So that's a direct relationship again. Now, there's one thing that we did mention. If the velocity, it's not just any kind of movement that's going to work. Remember I said that if I moved parallel, then we're not going to get anything created because we're not seeing any change in our magnetic flux. We're just having the same magnetic flux the whole time. So that means we also need to consider a fourth factor, which is the angle between the wire or the conductor and the field. So that means I'm considering theta here. So in fact, our EMF is direct. Why do I keep doing the wrong E? Sorry about that, people. It's proportional to the sine of that value of theta. If we put that all together and define our units in such a way, we can have an EMF that is equal to BLV sine theta. So now this allows us the possibility of finding the magnitude of the EMF when we have a current carrying conductor moving in a magnetic field. Okay, so the EMF for a current carrying conductor moving in a magnetic field. And we apply our hand rule, just like I did before, from the last unit to figure out which is going to be the positive end, which is going to be the negative end for the potential difference. Okay, tune in for a couple examples coming soon.